Okay, so last time we got into some concentration units, and obviously molarity is the big one, which is moles of solute per liter of solution. And remember, again, if you think of this as sort of a formula, so if you need moles, that will be liters times molarity. If you need liters, that will be moles divided by molarity. As we talked about, when you're doing sort of a calculation involving molarity, it's really a good idea to get rid of that big M and really turn it into really a conversion factor and take more of a dimensional analysis approach. So that would be 2.5 moles per liter, our liters on top if you needed to kind of flip it around and use it as a conversion factor to do it like so. Super important because, as I mentioned a number of times last time, it is really, really common when people kind of just leave the big M. They really just forget about the volume aspect of it and not sure, what they should do with the volume. Also, really important, as we talked about, is if you are going to use molarity by itself and you want moles, you do need to make sure you convert your volume into liters. It's probably a really good process in general because usually moles is sort of your outcome you're looking for. Remember that if you do not and you leave it in milliliters and you times it by molarity, you will not get moles, but you will get millimoles, which again is probably about 1,000-fold factor off of what you're kind of shooting for probably in your calculation. So just keep that in mind. We talked about dilution. And dilution is when we add more solvent. A lot of times that solvent is water. The moles of solute before the dilution will equal the moles of solute after the dilution. And remember that the solute and the solvent together is what makes up a solution. So the solute is the stuff dissolved and is the smaller part of the solution. The solvent is the larger part, which is in a lot of cases water, but not always water. And there is a formula that goes with dilution, which is M1V1 is equal to M2V2. Again, more generically, C1V1 equals C2V2. But since molarity is the most common unit of concentration, usually M1V1 equals M2V2 is the one most people kind of use. And this is usually before the dilution. This is usually after the dilution, and the more concentrated on the left there, and less concentrated or more dilute on the right. Because we are adding more solvent when we do a dilution, and we look at the molarity, which is moles of solute really over liters of solution. And again, the solution is the solute plus the solvent. So when we do add more solvent, we're actually increasing the bottom part of our molarity expression, and that will bring our molarity down because, again, the bottom number there is getting larger, and when we divide by a larger number, we get a smaller molarity. Typically speaking, like I said, this is the more concentrated guys. These are the more dilute, but it really doesn't matter as long as you keep, obviously, the volumes of molarities that go together. We also talked about that if you want to in this formula and you're using this formula for a dilution, you can leave your volume in milliliters because it will work out okay. It just means that when you solve for volume, you'll get milliliters. If you convert it to liters, you'll get liters. And that's because, again, here, let's just say you were solving for V2. M1 would be molarity. And if you did milliliters on V1 divided by M2, which is molarity, the molarity cancels, you end up back to milliliters. If you were solving for M2, M1 would be molarity, V1 would be milliliters, V2 would be milliliters. Those cancel and you're back to molarity as well. So you can definitely, if you're using that equation and doing a dilution problem, you can leave the volume in milliliters. It's all good. It will cancel out correctly. But if you are not doing dilution, not using that equation, best to make sure you convert it to liters so everything cancels out. Now, we also then talked about really kind of solution stoichiometry. And solution stoichiometry really is the same sort of steps that we've done previously. Again, you're going to balance the equation. You're going to convert to moles. Remember, if it's a limiting reagent problem, you probably got to determine that as well. 3, again, do your mole to mole relationship. And lastly, moles to some other unit. So the main difference here is usually step 2 or step 3. Step 2 is very common that we use molarity and volume, much like in our titration sort of calculations. Since we know the molarity and the volume, we rearrange this and solve for moles by taking liters times molarity, and that's a very common one, as opposed to grams to moles like we normally do. And I would say again here on the back end, you could solve for molarity if you figure out if you know the volume, figure out the moles from stoichiometry. You could also, if you obviously use the moles for stoichiometry, you know the molarity, you could figure out the volume as well, and those are common endings, as opposed to as well the same normal common ending of moles to grams using the molar mass. So we can use all those type of things. Any questions on that there? Okay, so continuing on, the next thing we're going to talk about obviously is what we've been doing, everybody's favorite thing, which is titrations. And now that you're professional titrators, as I saw with a lot of light pinks in your flasks, a titration, as we talked about, is a technique that is used typically, again, when you have kind of a known solution. And what I mean by known solution is, you know, like something like the molarity, you know, the volume that you're going to use of it, and you have an unknown. And that unknown, you know, maybe you don't know everything about it. Maybe you want to figure out the molarity. Maybe you want to figure out the molar mass, like you did in your experiment as well. Maybe you just want to figure out the volume. And we use this sort of process as you did using a burette, and you add it here and you do your titration. And up in the burette, for example, could be a base. It could also be an acid up there as well. And down here you have an acid, or if you got an acid up in the burette, you would most likely have a base on the bottom. So obviously opposites here. And we obviously add one to the other until the reaction is complete. And the reaction is complete in a titration at the equivalence point. And at the equivalence point in an acid-base titration like the ones you did, that is the point where exactly the moles of the acid will equal the moles of the base. So that is the exact point where basically you completely neutralize what you got in there, which is why sometimes it's referred to as a acid-base neutralization sort of reaction, depending on the titration you're doing. But that's when they're equal. Now, obviously, as you saw, you need some way to know when you are near the equivalence point and when you should stop your titration. So indicator seems like a good one, right? And obviously, phenolphthalein, right, is the one that we use there in class. Perhaps word to spell on the next exam, right? There, phenolphthalein. I'm not even sure I spelled it right, but you should try. And phenolphthalein, as you saw, and most indicators do work over a pH range. And something like phenolphthalein works from a pH of 8.3, which is basic, to a pH of 10, which is also basic as well. It is colorless on this end of the spectrum and gets that lovely shade of pink that some of you saw as you head towards the other end of the spectrum. Here, actually not too far past 8.3, does it start to get a little bit pink. And the indicator is obviously used to indicate to us that the reaction is over, and that is usually at this point where we kind of use up all of our reactants. Basically, they're both kind of gone at that point, and that's where we typically want to stop. And some of you did have beakers that look like that, which was pretty good. Some of you had better ones actually than I think that picture there. And we can figure out all those things using solution stoichiometry, the balanced equation, things like molarity of the unknown, molar mass, the volume that is there. And as you saw, and as we might have talked about previously, that famous saying that a lot of you maybe even said, right, I just added, again, 1 drop and it went like super pink, right? And the reason for that is if you take 200B next semester, which I think I'm teaching, I'm not sure. But if you look at something which is known as like a titration curve, like the volume of base added versus the pH of your solution, when you do a titration similar to the ones you did, you'll get what is referred to as a titration curve that looks something like this. And you got your equivalence point here. And again, what happens, as we might have talked about, is as you continuously add sodium hydroxide, the pH starts to rise. And what we see is as you approach the equivalence point, you do see a fairly vertical rise to the equivalence point, and usually you'll actually see a jump in pH to the equivalence point. And then after the equivalence point, you'll see another sort of vertical jump past the equivalence point. And that's really important for example, why you see like, hey, I just added that one drop and again, it went super pink on me. And that is because as we go from say here to here, the volume is not changing a heck of a lot. So anywhere down there, if you just kind of draw a straight line, you're pretty much on the same volume here. But what is changing a lot as you approach the equivalence point is the pH, right? The pH goes from here to here. So there's a big change in the pH as you approach the equivalence point with not a lot of volume added. So you literally could add one drop and see it go from no color to super dark pink. And that is because, again, your indicator is working off a pH range of like 8.3 to 10. So when you do so, and maybe you miss your equivalence point by like a drop, and you find yourself way up here, your pH is now closer to over here, and that's going to be really dark pink, right, as opposed to super light pink, and you only missed it by a drop, right? Now, is there really a big difference between my location here and here? The answer is there's not really a big volume difference between those two locations, which means, like I told you, you don't really have to redo your titration because it got super pink. Some teachers will make you redo it because you got really, really dark pink. And the reason they will sometimes make you redo it is if you really weren't careful and you titrated like I titrated when I went to school, which was just open that thing up and get cool dark pink. I'm done. I'll see you next week, right? I could definitely be like way over here, yes, and that is also a similar pH, which means my solution is going to look just as dark pink as yours. But the problem is, am I now near the equivalence point volume? I'm way away from it, right? And if I wasn't really careful and just open that thing up, I could find myself way away, and you probably should retitrate at that point. But if you did that, you probably don't care anyways because you just open that thing up and let it go. So that's why a lot of times teachers will tell you, hey, if it's not like light, super pink, you should redo your titration because they don't know if you were really clarifying just super missed it by a drop or you just opened that thing up and did it. Now, the reason we use something like phenolphthalein is for most of those titrations that you did, your equivalence point is probably in this ballpark, 8-ish or so. And that's why they tell you to go as colorless as you can, because that should hopefully stop you. As soon as you see that very faint color of pink, that should hopefully stop you near the equivalence point and put you near where you want. But more importantly, as I told you, and as you hopefully did, you want to look really more at the volume you use for each trial, and hopefully they should be about the same volumes that you use for each trial. Any questions on that there? All right. That was titration background 101. All right, so what is the molarity of a 25.5 milliliter HCl solution if it took 45.5 milliliters of a 0.25 molar sodium hydroxide solution to reach the equivalence point of titration? So let's kind of go through this. This, again, pretty much titration problems are stoichiometry problems. They're just solution stoichiometry problems. So we'll run through our steps here. We want a balanced equation. And obviously here it's going to be between our acid and our base. So we're going to take a little HCl and sodium hydroxide. Remember, this is an acid-base reaction, which means it falls under the double displacement banner. And one of the things you should know is you should always get two things when you take an acid and a base. You get water formed, and you also get a salt, which is the sodium chloride in this case. So again, typically the water is made from the acid and the base, and it's made from the H of the acid, and the OH of the base is my water. And obviously our salt here is going to be made by the other two components that are left over when they do their switch, our sodium and our chloride coming together here to make our salt in this case, right? So it is double displacement, and doing stoichiometry, we need the equation. We also want to make sure it's balanced, and in this case, it is balanced. We're all good on each side. So now we want to think about, what's going on in terms of the information that they gave us. So just get rid of some of these extra things here, maybe. Go. And got it. All right, so what we do know, again, in terms of the HCl, is we do know the volume here, 25.5 milliliters, and we are looking for the molarity. For the sodium hydroxide, we know the volume is 45.5 milliliters, and we know the molarity is 0.25 molar. So the first thing we want to decide is this a limiting reagent problem, right? So whenever we're doing stoichiometry, we want to determine, should this be a limiting reagent problem? And in this particular case, it is not, because we could only get to moles of this guy. There's no way to get to the moles of the other one. So this is just a basic stoichiometry problem, which I would say most titration problems probably are going to be. And that means we really don't need to do an ice table, because it's more work than it's worth, and you don't need to really do it for this type of problem. I would kind of only do an ice table for a limiting reagent type of situation. It's probably the best approach. For a basic stoichiometry, I'll just do the basic 4 steps that we talked about. So that means we are going to convert to moles, which is our next step. And this is, again, the only thing that we can convert to moles. We also want to think about the HCl, and we think about molarity. So clearly I do have the volume, but I don't have it in liters. That's easily solved. I am looking for the molarity. So really the one thing I'm kind of missing to get there is the moles, and that's where the stoichiometry is going to come from. So we're going to use the sodium hydroxide here to do stoichiometry to get the moles of the HCl. So since we are using molarity here, we do want to maybe convert it into just a usable unit, get rid of the big M. And again, you can flip it around and use it in the other direction if you need. We do need to convert our 45.5 milliliters into liters. So that's 1,000 milliliters is 1 liter. You can move the decimal place 3 places to the left if you like as well, and that will give us our 0.0455 liters of sodium hydroxide here. So now we can use the molarity. And again, one of the nice things about doing dimensional analysis is I don't even have to worry about this equation or rearranging the equation. All I have to do is go opposites cancel. So liters are up on top. So clearly we need liters in the opposite location. So I would want to use the molarity just like it's written, moles per liter. And remember, when you're doing dimensional analysis, everybody on top gets multiplied, everybody on the bottom gets divided. So you grab a calculator wherever you dropped yours. And 0.0455 times 0.250. That is going to give me 0.011, I'll call it 38 moles of sodium hydroxide. Any questions on that so far? Now, I'm not interested in sodium hydroxide, right? Because I need to get over here to HCl, right? To get the moles of HCl. So we're going to use the stoichiometry and do our mole to mole relationship here from the equation. And from the equation between HCl and sodium hydroxide, it is a 1 mole of HCl gives us 1 mole of sodium hydroxide. So that's a nice 1-to-1 ratio there. So taking our number that we got there, 0.01138 moles of sodium hydroxide, using our mole-to-mole relationship, 1 mole of sodium hydroxide, 1 mole of HCl. Moles of HCl are going to cancel. I think I could do that. It's still the same number, 0.01138 moles of HCl. So again here, we're using the stoichiometry to get to our moles. And that is going to bring us to our fourth step here, which is we're going to take those moles to some other unit. And at this point, we now have the moles. We have basically the liters. So all we have to do is basically put it in there. Before we can put it into our molarity equation, we obviously also need to convert our volume into liters as well. So this is 25.5 milliliters. Also divide by 1,000. It's going to give us 0.0255 liters of HCl. And now we can get the molarity, which would be our moles from the bottom there, 0.01138 moles, divided by our volume in liters, 0.0255 liters. And if we do that there, we're going to end up with 0.0255. And we'll call it 0.446 molar HCl. So here, really our same 4 steps, convert to moles, moles to mole relationship, and moles to some other unit here. Any questions on that? Yeah. So the answer is going to be yes, but no. So you shouldn't use it. Okay. So you should show it through stoichiometry, and that equation is really for a dilution equation, even though online people sometimes call it a titration equation. It is a titration equation in the sense that, like you found, perhaps you will get the same answer, but you will only get the same answer if it's a 1-to-1 relationship. So if your stoichiometry between your acid and base is not a 1-to-1 relationship, you will not get the right answer using that. So I'm going to say don't use it for this application, even though the one place where it will come out the same is in this like situation 1-to-1. But definitely if the relationship between acid and base is not 1-to-1, you won't get the right answer. Yeah. You could do all that, but you might as well just do the stoichiometry if you're just going to have to adjust it anyways, right? So for us, for a titration problem, if you want all the credit, you need to show it through stoichiometry, okay? And again, definitely won't get the right answer, and you can obviously adjust it based on the coefficient and all that. But if you're going to do that, you might as well just show the work the right way. Yeah. Other questions? All right. So why don't you try this one here? What volume of 1.4 2 molar sodium hydroxide is required to titrate 25 milliliters of 4.5 molar sulfuric acid? So give it a go, see what you come up with. And we're going to need an equation, so we'll start with that. H2SO4 sulfuric acid plus a little sodium hydroxide. Again, it's going to be a double displacement here, and we should definitely get water formed. And our salt's going to come together. Remember, we do want to make sure we get the right formula first. So when sodium and sulfate come together, that is what you get, Na2SO4. Now that you did that, we then need to make sure we have it balanced, and we will need a 2 there, and I believe maybe a 2 right about there as well. So now we have our balanced equation. Again, remember that you don't want to try to balance and write the formulas first. You want to do formula first and then balance. If we take a look at what's given to us here, we're looking for a volume of sodium hydroxide. We have the molarity given to us. For our sulfuric acid, we have the volume given to us here. And we also have the molarity of 4.5 molar. Once again, we could definitely get moles here, no chance of getting it there. So once again, like most titration problems, just a basic titration type problem or stoichiometry problem. So we're going to go to our next step, which is convert whatever we can into moles, and that's going to be this guy here. Once again, we're going to divide our volume by 1,000 or move our decimal, and that will get us to 0.025 liters. We'll use our molarity by getting rid of the big M and converting it into moles per liter. And again, in this case, we do need liters on the bottom, so we'll go with 4.5 moles per liter of sulfuric acid. The liters are going to cancel. And if we get an answer here, 0.025 times 4.5 looks like 0.1125 moles of sulfuric acid. Once again, if we think about the sodium hydroxide, which is ultimately where we're trying to get to, and we think about molarity, we obviously do have the molarity given to us. We are looking for the volume. So once again here, we're really just using stoichiometry to get to the moles of the sulfuric acid. I'm sorry, the moles of the sodium hydroxide in this case. So the next step is our mole-to-mole relationship and looking at the equation between these two. It is a 1-to-2 relationship. So for every 1 mole of sulfuric acid, you get 2 moles of sodium hydroxide. Once again, just the coefficients in the equation. So 2 moles of sodium hydroxide up on top. Opposites cancel, so 1 mole of sulfuric acid on the bottom. Again, we're multiplying and dividing here. That means that the moles of sulfuric acid will cancel, and we will hit the wrong button there and come back, maybe come back. There we go. Where are we at there? There it is. All right, and so we'll take our number there, times it by 2. Gonna get us here 0.225 moles of sodium hydroxide. Any questions so far? So again, just our basic steps here: balanced equation, convert to moles, mole-to-mole relationship. Last step is, now that we have the moles of sodium hydroxide, we could put it there since we already also have the molarity here, so we could solve for the volume. I again am going to convert my molarity of sodium hydroxide into both units and use it like a conversion factor. So number stays with the moles, always over 1 liter. Or again, you can flip it around and use it as a conversion factor that way. So if I take my moles of sodium hydroxide here, and again, just kind of do dimensional analysis, we want moles on the bottom. So we do actually want to use it in the flip version. And we're going to put 1.42 moles per liter sodium hydroxide on the bottom. The moles are going to cancel, and that will get us here, looks like 0.158 liters of sodium hydroxide. If you times that by 1,000, that is roughly 158 milliliters of sodium hydroxide. And that would be like step number 4 there. Any questions on that one there? So again, just basic stoichiometry, just kind of how you get to moles, usually slightly different. And obviously at the end, maybe solving for something other than grams at the end of the calculation. Any questions on that? As to the earlier question, again, here, if you just use M1V1 equals M2V2, you would be off in this case because, again, the relationship is not a 1-to-1 relationship if you didn't do any type of outside adjustment. So again, make sure you show it with stoichiometry if it's a titration type problem. Questions? I say that for your own good so that you don't put the wrong answer and that's the only work you show and get a 0 on the problem. Yeah, so make sure you show the equation, all that stuff through stoichiometry. All right, one more here. Maybe what is the volume of 0.15 molar phosphoric acid that's needed to neutralize 45 milliliters of 0.55 molar KOH? So let's take a look again. We're basically doing a titration problem. Sometimes they'll come straight out and say titration, but they'll say neutralize or something like that. It's basically a titration problem. So once again, we're going to start with our equations. So we have our phosphoric acid in this case, reacting with our potassium hydroxide. So that is our acid plus our base. Once again, gonna do a double displacement here, switch partners, and that will give us water like normal usually. And remember, we do want to put this together correctly. So potassium is +1, phosphate is -3. So you need 3 of those guys to balance it out, giving you K3PO4 again as the proper formula here. Once we do that and we have the right formulas down, it is balancing time, and I believe a 3 there and also a 3 by our water should take care of business, I think. Any questions on the formula here? All right, so again, being able to write these formulas or equations are really important. So if we take a look at what was given to us and what we're trying to find, we are trying to find obviously our volume here. We do have the molarity, which is 0.15 moles per liter. For our KOH, we do have the volume, 45 milliliters, and 0.55 moles per liter here. So once again, we definitely could get to moles here, and that's the only thing we can get directly from moles. We are looking for volume, so molarity is obviously involved, and we have the molarity. We're looking for the volume. So once again, like kind of normal here, we're going to use stoichiometry to get to the moles part that we need to basically finish the calculation. So we'll start with our moles. So we're going to convert our volume into liters. Again, divide by 1,000 or move your decimal place 3 places to the left. We will use our molarity of the KOH. And here we do want the liters on the bottom so that they do cancel out. And if you get an answer at this point, you're looking at 0.0450 divided, not divided, times 0.550. Going to give us 0.02475 moles of KOH. Once again, we're not interested in KOH because ultimately we need to get over here to phosphoric acid and figure out the moles of that. So that is where our third step in our stoichiometry will come into play. The relationship again from the balance equation for these two. For every 1 mole of phosphoric acid you toss in there, you need to also toss in there 3 moles of KOH. So that is our stoichiometry relationship here. Opposites cancel, which means the 3 moles will go on the bottom. The 1 mole of phosphoric acid will go up on top. The moles will cancel. Here we're basically dividing by 3. So anything on the bottom gets divided. And that will end up with 0.00825 moles of phosphoric acid. Any questions up to that point? Again, really just stoichiometry, balance equation, convert to moles, mole to mole relationship. So again, just the same sort of 3-4 steps that we've been doing. At this point, we now have the moles and we have the molarity. So we can use both of those together. So I'll take my moles of phosphoric acid, which is this number here. We will use our molarity here as a conversion factor. So in this case, we actually do need to flip it. So moles are on the bottom and that would give us 0.550 moles per liter of phosphoric acid. And again, we're dividing what's on the bottom, multiplying whatever's on top. So in this case, we're actually going to divide by 0.55. And that's going to give us here 0.0150. And the units here would be liters at this point. And if we want milliliters, once again, a liter is 1,000 milliliters. So something like 15 milliliters in this particular case. Question on that problem there. And again, this would be equivalent to our fourth step of our problem. So hopefully you can see titration problems are really just stoichiometry problems using volume and molarity. And again, the stuff that you calculate at the end, sometimes we'll also use molarity as well. Any questions on how to do those problems there? And obviously, similar calculations for the experiment we've been working on, obviously, as we've gone through. All right, so now we talked about titration. I think we'll skip that one. We did one similar. We're going to also talk about a couple other type of concentration units that might not be used as much, but are still obviously good to know. And the first one is percent mass to mass. This is sometimes referred to as percent mass to mass, or abbreviated percent m/m. And obviously the two m's stand for mass to mass, basically. And to calculate the percent mass to mass, it is the mass of the solute divided by the mass of a solution, or the solution, times 100%. The important part when you do this calculation is actually the bottom. And again, a reminder that the solution is made up of two things, the solute plus the solvent. So you definitely want to make sure on the bottom there that you have the mass of both of those things, and that you're not just using the mass of the solvent. The reason that is an issue is a lot of times in these type of problems, they will actually break those numbers up. So they'll give you kind of the mass of the solute by itself, and they'll give you the mass of the solvent by itself. And sometimes they just won't give you the mass of the solution. So it's a very common mistake that people make, which is they just kind of roll with the solvent number and not the entire mass of the solution. And you times it by 100% there, and I'll give you your percentage. So if you did have, for example, a 4.5% by mass sodium chloride solution, and you're actually given the percent by mass and you want to do a problem, sometimes it's good to kind of take a dimensional analysis approach to those calculations. Again, you don't have to worry about maybe rearranging the formula or anything like that. But what that would mean if you wanted to kind of turn that into a usable conversion factor is you would have about 4.5 grams of sodium chloride in 100 grams of solution. Or you could flip it around and use it in the other way. 100 grams of solution would have 4.5 grams of sodium chloride. So you could use it as a conversion factor there. As I sort of ran out of room there, so go 4.50 grams of sodium chloride. And mix that there, 100 grams of solution up on top. And 100 grams of solution up on top. And again, I would take it as a more dimensional analysis approach, and you don't have to worry about sort of rearranging the equation here. So we assume 100 grams of solution because it just keeps the number the same, so you don't have to change any of the numbers, basically. And this is basically grams divided by grams times 100. So why don't you try one here? A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. What is the mass to mass percent, basically, or the mass percent? So let's take a look. We're looking for the mass percent here. And again, that is the mass of the solute over the mass of the solution times 100%. So in this case, the calcium chloride is our solute. It is the smaller part of the solution. The water here is our solvent, is the larger part of the solution. And that means that we do have our mass of our solute, which is 2.5 grams. We do have the mass of the solvent, which in this case is 50 grams. And again, both of those things together is our mass of our solution. So again, we want to make sure we do add it together to get the mass of the solution, and that would be 52.5 grams. Again, that's an important number because that is what should go on the bottom, not just 50, which is just the solvent by itself. So if we put in our numbers here, 2.5 grams up on top, 52.5 grams on the bottom, times 100%. That's going to get us something 2.5 divided by 52.5 times 100. Can give us 4.76%. You could leave it M/M, and you could put something like calcium chloride next to it, would be nice. And that would be our mass to mass percent here of this solution. Any questions on that? Yeah. Yeah, I would, you should probably identify what percentage it is, because let's see here. There are, in addition to mass percent, a couple of other sort of percent concentrations. So there is, for example, percent V/V, which is volume percent, and that is the volume of solute over the volume of solution times 100%. So it's usually kind of milliliters over milliliters here, and they will cancel out, and it's usually just a percentage. So there's also percent mass to volume, M/V, and that is the volume of solute over the mass. I'm sorry, I went backwards on that. That is the mass of the solute there. That's the mass of the solute over the volume of solution times 100%. This is almost like density is grams typically over milliliters is typically the units associated with that. And along with obviously the one we just have been doing here, which is our mass to mass, which is the mass again of our solute over the mass of solution times 100%. And again, that's kind of grams over grams. So because there are these different ones, you should kind of display which one you're talking about, so they have a reference of sort of what that number is. By the way, they all work the same. In these guys here, you don't really have to worry too much about the bottom, because typically in those problems, they'll just kind of give you the volume of the solution rather than break it up. It's really just the mass to mass one. They very commonly will break up the solute and the solvent that you have to worry about it. They all work the same. So if you had a 4.5% volume to volume, that's the one they kind of use for alcohol, right? Percent by volume. That would mean that you have, say, sodium chloride. You would have 4.5 milliliters of sodium chloride in 100 milliliters of solution. And you obviously could flip it around the other way as well. And if you had a 4.5% mass to volume sodium chloride solution, you would have 4.5 grams of sodium chloride and 100 milliliters of solution. And once again, you could also flip that around and use it as a conversion factor, just like we kind of did here with our other ones. So they all work the same way. You can kind of plug and chug in there, but they are different in terms of what they're looking at. Obviously, one's looking at just volume to volume, mass to mass, and mass to volume on the other one there. Any questions on that there? All right, so let's take a look at another one here. Concentrated hydrochloric acid contains 37.2% by mass hydrochloric acid. What is the mass of HCl that's contained in 35.5 grams of the solution? So let's take a look. So clearly we're given a mass percent, so we could think about our formula here. And again, going to be our mass of the solute over the mass of the solution times 100%. In this case, we are given 37.2% by mass. And we have the mass of the solution, which is 35.5 grams. We're looking for the grams of the HCl. How would I know if it didn't, for example, say solution there? I would know that the grams of the HCl is the grams of the solute, because remember that the name of the solution is usually the solute. So if you're looking for this name of the solution there, how many grams of that, it would definitely be the solute. You definitely could plug and chug into this equation, since you do have this, you do have that, and you could obviously solve for the mass of the solute. You could also, again, like we were talking about, kind of turn your percentage into a conversion factor. So 37.2 grams of HCl in 100 grams of solution, or again, 100 grams of solution would contain 37.2 grams of HCl. And again, if you do that, you could just kind of take the dimensional analysis approach, not worry about rearranging this equation if that's something that maybe you struggle with. And again, just do a dimensional analysis. So grams of solution are on top. I need them on the opposite location to cancel. So it has to use it like so. That way the grams of solution will cancel. Again, multiplying the top and dividing the bottom there. And we'll take 35.5 times 37.2 divided by 100. Going to give us about 13.2 grams of HCl in this case. Yeah. Obviously, if you just plugged and chugged into the equation, you're basically doing the exact same math as well. You should get the same answer. Any questions on percent concentrations? The last thing we're going to look at, I think here, or last two things we're going to look at, is molality. And molality is different than molarity, so don't get the two confused. Molality's kind of symbol is lowercase m, so that's not mass when we're dealing with it. It's actually molality. And the definition of molality is moles of solute divided by kilograms of solvent. And towards a later chapter, we will see molality used a lot when we deal with solutions and colligative properties. And again, not to be confused with molarity, which is moles of solute and liters of solution, and also a capital M. By the way, the thing that ties both of those together, in case you need to go from one to the other, is something like density. Can allow you to kind of go back and forth between those two units. So typical here, moles, typically got to do your grams to moles conversion. And obviously you will have just the solvent you're looking for here, and it does need to be in kilograms. Kind of like we say molar for molarity, molal for molality is used. So if we take a look at one here, calculate the molality of a solution prepared by dissolving 61.7 grams of C3H7OH in 175 milliliters of water. So again, if we're going to be looking at this, molality is our moles of solute over kilograms of solvent. And obviously, whatever we're dissolving will definitely be our solute. And in this case, water is going to be our solvent in this case. So like normal, in order to get to moles, we do need to convert those grams into moles. So that is C3H7OH. So that is 3 times 12.01 for the molar mass of carbon. There are actually 8 total hydrogens there, 1.008 each, and 1 oxygen at 16 grams per mole. And if we add all that together, 3 times 12.01 plus 8 times 1.008 plus 16, going to give us a molar mass here of 60.09 grams per mole. So taking our grams, 61.7 grams of C3H7OH Just going to do a grams to moles conversion. So we'll put our grams on the bottom here and our moles up on top using our molar mass from the periodic table. So we're going to divide 61.7 divided by 6009. Going to get us a 1.027 moles here. Now, in terms of our solvent, we got 175 milliliters of water, but we need kilograms. So obviously, to go from there, density seems like a good thing to use, and this is the density of water, and it is 1 gram per milliliter, which makes the math not too bad. That means I got 175 grams of water. Remember, though, that it does need to be in kilograms on the bottom there, not grams. So again, 1,000 grams is 1 kilogram. And that's going to get us 0.175 kilograms. So now we have our moles and we have our kilograms of solvent. That is everything that we need. So if we pop it in here, we get 1.027 moles divided by 0.175 kilograms. And that will get us here, looks like, we'll call it 5.87. Now the units here do not cancel out, so you can leave them moles per kilogram. Kind of like molarity, the number stays with the moles part is 1 on the bottom. Or you can, just like you do kind of with molarity, you can just use the little m if you like at this point, just like you kind of use the big M for molarity. So either one of those is a way that we can use that. And like I said, we definitely will see this a lot with colligative properties in chapter 10, I think it is, maybe, when we talk about those kind of guys. Questions on molality here. The last thing for sure in this chapter here that we're going to talk about is mole fraction. And mole fraction is also another thing we'll see in a couple of other chapters, including the next chapter, which is gases, and also in that colligative property chapter. Mole fraction is essentially abbreviated with an X. So if you had moles of A plus moles of B in something, you could calculate the mole fraction by taking the moles of A divided by the total moles. It's a percentage without a percentage, so you don't times it by 100, so you get like a point something or a 1 for 100%, right? So it's basically just like a percentage, but without multiplying by 100 in this case. And it basically will tell you, obviously, kind of the percentage of moles you have of each of those substances that are present. So if we take a look at it here, this example, calculate the mole fraction of methyl alcohol in a solution that has 0.328 moles of methyl alcohol and 0.929 moles of ethyl alcohol, also known as ethanol. So here we could get our total moles by frankly just adding them together. So if we take our 0.328 plus 0.929, that will give us a total moles of 1.257. And now we can really calculate our mole fraction for each of these if we wanted to. The mole fraction, which is abbreviated with a big X, would be the moles of methanol, which is 0.328, divided by the total moles here, 1.257. Again, we're not multiplying by 100 here, so we will end up with basically 0.2609. We could do the exact same thing for the other one, which wasn't asked for, but we could. And we could take the moles here of the second component divided by the moles, total moles. And again, if we do that, we will end up with 0.7391. We also could have, because these are the only two components, did 1 minus 0.2609. That's the same thing as doing like 100 minus a percentage and end up there as well. Yeah. So basically what this is actually telling you is like a percentage. This thing is made up basically 26% of those moles of methanol and about 74% of ethanol in this particular mixture. And again, mole fraction we'll see in the gas chapter, and we'll also see later on as well. Clearly, this problem gave it to us in moles, but if it's not, you may have it in some other unit like grams. You have to do a grams to moles conversion, and then obviously you can calculate your mole fraction question on that there. All right, that wraps up this chapter. It's good.